it's an honor to be here today. To all of our friends that are here, our customers, our partners, our prospects. We know how valuable your time is, as David mentioned, and we deeply appreciate you being here, coming all the way to Vegas, in some cases from across an ocean. And our goal is really to make every moment here worthwhile and filled with useful information. So I want to start with a big thank you to the team at Cockroach Labs who put this together and invested this event with so much energy and purpose. And also a heartfelt expression of gratitude to our partners. We have a special thank you to AWS, Osed, Teleport, and Ori. So we also had the great pleasure last week of announcing our new partnership with IBM at their Tech Exchange event in Orlando, and I was able to go down there. And really what we see as the real importance of this partnership is it's a strategic investment in joint customers in helping them modernize with confidence. That's sort of how we introduce this at the Tech Exchange. And the goal here is together to deliver resilient, cloud agnostic, and I'll say it, AI-ready infrastructure. We're global again this year. Last year we did London, we did New York, we did Palo Alto. This year we've changed it up a little bit. We've done India for the first time. That was in Bangalore. I had the pleasure of going out to India in September for that event. And now we're doing Las Vegas, right next door to Oracle World. So that's been interesting. I hope everyone here who has seen the billboard out there, sure to get some reactions. Our reach continues to expand. We're very pleased to be building this momentum together with all of you in the room. So you're going to hear after me, and I think this is the most interesting part of RoachFest, from some of our marquee customers. And that's going to include FanDuel, Squarespace, Cisco AI, and our partner IBM. And we actually have a very special keynote from a very distinguished guest, Kelsey Hightower, from Google and Kubernetes fame, amongst other things. And he's going to share some insight from his 20 plus years in the industry, building systems that outlast chaos. So very much in keeping with what we're all aiming to do in this room together. And then we'll close with a great reception today, and I hope all of you come up and I have a chance to meet you. So this year, our theme is simple but powerful. Performance under adversity. David mentioned this. Both performance and, of course, resilience are critical requirements for use cases today. Doing them both well is the essential challenge, and it's why we're all here today. It's customers from the very earliest days of Cockroach to the most recent have routinely cited resilience as the #1 point of differentiation that makes Cockroach the appropriate choice. It has to, by the way, be a first-class design principle. Like, we started out naming this database Cockroach because we recognize that essential requirement. You can't just bolt on resilience as an afterthought. And by the way, almost every other database has tried to do that. It actually has to be architected into every facet, into every level of the database, from the lowest levels of the stack all the way up to the highest. Because the weakest link in all of those components that work together is going to be the level of resilience that's delivered. It also, by the way, goes far beyond what we can directly control in the database's sort of innards. We're subject to environmental faults that are somewhat outside of our control. And of course, applications can misbehave. But there's lots of defensive steps that we can take as we start to experience these problems along with our customers. And ultimately, we can become more and more defensive and build excellent capabilities where we can accommodate even poorly behaving environmental and application faults. So we have the theme last year was actually state-of-the-art resilience, and we introduced a lot of what I'm going to show you on the next slide here. This is a concept that really does involve two facets to really build the gem here that is of high value. On one hand, you have high availability. And really the way I think about that is this taking circumstances that used to be the cause of disasters that you'd have to recover from, and it's moving those into the realm of IT resilience. Can we have total business continuity without having to do postmortems, without having to potentially deal with data loss or regression? And the key to that is multi-active replication. This is the inherent capability where you're relying on consensus to create a much more resilient system in the event that all kinds of potential disasters come to pass. So this is about autonomous failover, no human in the loop, done at machine speed. And it's about self-healing recovery, and all of that with a zero recovery point objective. But there's also a bunch of other features. It's sort of a grab bag of them that we're constantly adding to that we kind of group into this idea of advanced fault tolerance. There's lots of crazy circumstances and edge cases that do happen in production. And this is where we've come up with ideas like the write-ahead log failover, and also our internal routing capability to essentially route around asymmetric network partitions. And then there's logical data replication. This is a fundamental recognition that you can't always have tightly coupled systems. You might have military field applications. You might have cruise ships all over the world that have fairly inconsistent connectivity. You might have part of your business that's running in China, and you want to work around the Great Firewall. So loosely coupled systems do allow some pretty advanced network topologies or deployment topologies. Now, on the other side, we've got disaster recovery, because the reality is that no matter how far you move the goalposts in terms of building towards IT resilience, there's always the next step of a disaster. You've lost multiple data centers, you lose multiple regions, you lose multiple cloud providers. That kind of a situation does necessitate a restore from a backup. And so how can we build defense in depth, make better backup, have point-in-time restore on the recovery? And also, we've introduced an online restore capability that goes direct to the backup files instead of potentially waiting for a lengthy recovery phase where you're moving from the backup to the primary storage. So meanwhile, when you're needing to access data, you're going first to the backup, and then that gets cached locally. So the locality of the data allows that kind of high latency startup period to be quickly mitigated as data is accessed. And then in the background, you do the normal restore into primary storage. So it's a very clever system. Also, physical cluster replication. So this is kind of what was old is new again, in a sense. This is providing very transactionally consistent sort of hot swap failover capability for Cockroach. Again, defense in depth. This isn't what you want to primarily rely on, but it's a great thing to have as a backup. So this state-of-the-art resilience, this is absolutely not a static goal, right? We're constantly moving to keep the bar rising, to stay ahead of the customer expectations. And ultimately, every single thing you saw on the previous slide was a direct response to our own experience, to our customers' experience. And your toughest challenges are fundamentally what are driving the highest priority items on our roadmap. And it's events like this one, RoachFest, and the CAB that we held yesterday that really help us understand your challenges. The customer perspective is truly crucial in terms of also how we measure and test resilience. Like, what does success constitute? So thank you all for helping us build a better database, because it is getting much better, and I'll show you some of the amazing progress. So what's at stake? We actually recently did a survey, sort of a study, and we surveyed close to 1,000 industry executives across many verticals, primarily focused at the enterprise. And based on those responses, we actually collected some pretty interesting and frankly eye-watering results here. We saw that the per outage losses went anywhere from 10K, that was sort of the low end, all the way up to 1 million. And anecdotally, we've had customers that have cited millions, even for minutes of downtime. So, and actually, in addition to those direct costs in dollars and cents, there's some indirect costs that are actually quite significant. For example, you can have reputation brand damage. You can also have the morale of the teams that are scrambling constantly to handle these and handle postmortems for the applications. And then, of course, you can have increased regulatory scrutiny, which nobody wants. The outages were also surprisingly frequent. We saw, on average, across these close to 1,000 surveyed respondents, that there were 86 outages a year. And that's more than one a week. And they're actually often sustained. Now, this says 324 average minutes of downtime, but this is actually because when you lose something like a data center, you might have 50 use cases that are down. So in aggregate, these minutes do add up. And this is 5.5 hours of weekly downtime, not yearly, weekly. Now, that's fairly shocking. You can see how the numbers add up. And this is not an aspirational goal anymore. I think that's why you're all in this room. But I think this is dawning more widely in the industry. This is actually a business mandate. And by the way, consumers today are expecting these always-on experiences. The idea of having maintenance windows and planned downtime, this is old hat, right? And business leaders are expecting better results. Regulators are also expecting better results. And for mission-critical applications, the new gold standard is definitely to achieve 5 nines of availability, which, by the way, is only 0.1 hours of downtime a year. That's a pretty insane number. Now, things like mainframes offer 7 nines, so that's quite interesting. But the reality of this is, what can you achieve in the cloud? That's where everyone is looking to increasingly run their use cases. And 5 nines is only possible when you can survive regional outages. Now, everyone in this room has probably read more than their fair share of marketing literature about databases. Lots of claims out there. In fact, it seems that every database is resilient, every database is scalable, every database is highly performant. So it's very hard, unless you're a database expert, to really parse these claims and come to a definitive conclusion about what ought to be chosen. And we looked at this morass of claims and realized that a lot of the claims we made 10 years ago are being made more broadly in the industry. And we really wanted to actually try to bring some proof, some receipts of what the reality is underneath the claims. And one realization we had is that benchmarks across the industry are just routinely and maybe exclusively measured under idealized conditions, right? Almost like laboratory pristine conditions. The reality of the world is that it's messy and extraordinarily chaotic. Like I think this Tough Mudder race on the right is kind of how it feels to be in the trenches day in, day out over the course of years. Performance benchmarks fundamentally need to reflect this reality. And so that's what we did. We introduced a better framework, a better benchmark, and we call it performance under adversity. And it's really a performance benchmark that aims to understand what happens to performance when you go from perfect conditions to sort of normal conditions, which are not perfect, they're messy, to bad, to worst, to worst. And in this slide, what you see is a series of what we call adversity phases. And they're listed from bad to worst, from the left to the right. Now you can see the first is this nice little green section. By the way, these idealized conditions here, they sort of set a baseline for your performance. But this is really where most benchmarks start and stop. This is all you see. By the way, the graph below here is showing some very important metrics that go along with over the course of that phase being run. And by the way, this is TPCC running underneath. So this is a very venerable database benchmark. And what you see on the bottom here in the blue line is the throughput, the sustained throughput, how many SQL requests per second. And then you have P90 and P95 latencies all the way down there at the bottom. And these graphs here are what you see with Cockroach when you're just running the benchmark with no other stress on the system. And these are idealized conditions, so it's not really that surprising that these graphs are as smooth as they are. That's certainly what we'd expect. But of course, what happens when things start going wrong? So the next phase on adversity, and it's the longest one, this yellow phase, it's actually measuring what we call the internal operational stress. In other words, these are like the normal day-to-day conditions. You're always seeing these things happen, day in, day out. And they include things like running a full backup on the system, like running change data capture, which is a continuous consumer of IOPS and CPU in the system. It includes a schema change on the largest table in the TPCC benchmark, which is the orders table. So, by the way, some databases can't even do that without locking things up, but we're running the full benchmark while we're doing this schema change. And finally, there's an upgrade. This is a 15-node cluster in this particular example. We recycle all the nodes in a rolling restart, and we upgrade the database. Again, something that you would never do when you were running a benchmark in sort of traditional perspective. And each of the circles at the top of the graph represent different events where things could go wrong. But what you see here is that there's fairly extraordinarily smooth results. So what happens on the next phase? Here's where we actually start to introduce more extraordinary circumstances. These are distalls. And so what is a distall? It's not a direct error from the underlying storage devices in the system. It's actually a gray failure. So the disk starts to become very slow. It maybe start to dribble I/O. So it might go from a very healthy amount of megabytes per second, and it goes down to bytes per second. And many databases get extraordinarily confused by that, but it turns out that these kinds of failures are extremely common in the public cloud when you have network-attached storage. And how common? Well, it's once in a million writes, or once in a million reads. Well, that doesn't sound very bad. But let me tell you, a million reads on a scaled-out Cockroach cluster happens in several seconds. Right? So you actually see these all the time. And when we actually introduced some of the fixes like write-ahead log failure to address this problem, we saw customers' latency graphs, which had a lot of spikes at the P95, P99, and they just smoothed out. So in fact, people were seeing this all the time. Customers were feeling this is random, slow, like why is this page taking a long time to load? That's a big cause, is these EBS volumes that didn't work so well. And interestingly enough, when we complained, this affects all the clouds, not just AWS at all. But we said, hey, we're having this problem. And they said, well, that only happens once in a million writes. And it only happens on GP3. You can move to a more expensive and better version of this EBS. This actually is a wonderful feature in that you get to continue to use the more cost efficient, but you still get the perfect performance. So actually, in this particular test, we subjected every single disk used in the cluster to multiple 10-second stalls over the course of this testing period. And there's virtually no impact on throughput and latencies. By the way, that's not the way it used to be before we introduced this feature. The results were considerably worse, as they are in almost every other database on the market. So next up, we have network failures. In this, we tested full network partitions. We tested the more insidious variety, where you have a partial asymmetric network partition. So in other words, node A can not see node B, but node B can see node A. That creates a lot of confusion in the system. And again, you might think that's pretty rare, and certainly it might be if you're still running in private data centers. But in the cloud with software-defined networking, these are surprisingly common. And we also have node failures. So now these are very distinct from the phase of the test where we do a rolling restart to upgrade the database. These are abrupt node terminations, no warning, and there's sort of a kill-9 on the process. And by the way, as you can see, there's very little visible impact here. That wasn't true. And Cockroach, if you're using a version just as recent as a year ago, you won't see these perfect results. And the reason is because we introduced something called leader leases. It's a very fascinating technical advance where we're actually moving some of our capabilities deeper down into the consensus algorithm. So smart engineering really can make incredible advances. Now we move on to zone failures. Here's where you start to see some results change, and it's in the P95 and P90 latencies. So what we're seeing here is an entire data center going out of commission. So it affects a much larger set of nodes, a fraction of the nodes in the cluster. And the beauty of this is, yes, there's some additional latency as node leases expire and things like that. But this cluster self-heals, recovers when the data center comes back online. Even before it comes back online, the system is healing as it just uses the remaining data centers effectively. There's no human in the loop. This self-healing process happens automatically. And then the final stage, the worst that we're measuring here, and there's still worse that could be measured, like you lose your entire cloud provider. But this is region failures. So this is an even larger fraction of nodes in the system. And there's a more extended period where the latencies are elevated for P90 and P95. But again, no humans had to be taking action. Right? The system is handling this with no data loss. Right? And it seamlessly self-heals both when it's getting used to the fact that a region is missing, and then when the region comes back, it's catching that region up. So ultimately, these results, and in the next slide, you'll see how much we've improved them, but the results in our endless process to make the system behave better and better are what help us all sleep better at night. So this is what this exact same benchmark looked like as recently as 25.1. That's only 6 months ago. It's just an idea of how much work we're putting into the system. And frankly, it's also a reflection of just starting to measure the right things. Like no other database vendor in the market is trying to measure exactly what performance looks like when these adverse circumstances occur. But the very act of starting to do it highlighted a bunch of areas that we could improve in. Right? So this is, you can see there's a lot of choppiness in the latencies here. And there's some perturbations in the throughput line. And 6 months later, we're seeing that the SQL latencies have improved by 10x. And the larger sort of TPCC operations that actually activate many individual SQL operations are about 2x better. So this is the consequence of some new engineering that was put into the system. So you can just look at the elevated latency. Even the baseline in the top graph is quite a bit higher than it is in the single-digit milliseconds in the graph below. So you may be very naturally curious about how competitors stack up here, and we have begun running very extensive evaluations. There's really one competitor that I think is worth calling out on here, and that's Oracle. So they last year recently introduced a competitive product called the Globally Distributed Database. I would just say that imitation is the sincerest form of flattery. I don't think their claims have been particularly well supported, but we actually aim to make our own claims and support them with hard data. And what we did is we engaged a third-party vendor with considerable expertise in running Oracle, both in the public cloud and in OCI, or the hyperscalers in OCI. And they were able to set up Oracle, and we ran it with essentially an extraordinary degree of chaos. And what we wanted to do was create configurations in Cockroach and GDD that were very, very close, as much apples to apples as we could. GDD is a fairly kind of legacy product, but it has a lot of things bolted onto it. And so if you want to have a truly scaled out system with GDD, your application has to manage the sharding manually. Right, so that means that in reality, like the key sort of replicated component is one shard in GDD. So it's a 3-node cluster. And that's exactly what we did with Cockroach. We did a 3-node Cockroach cluster, a 3-node GDD cluster. GDD requires all these other servers to be running to help coordinate everything. So it's a bit more complex to set up. But we put both systems through their paces, and we wanted to drive a really quantifiable comparison. So we are actually measuring the number of errors that were experienced by the client that was running the tests, and also the aggregate downtime. In other words, how much latency was introduced that went beyond timeouts in the system. And we aggregated that in seconds. And so what we came up with is a fairly remarkable chart here. And I'll say this, GDD is not the worst database on the market. Their results are actually better than some of the distributed database competitors, right? But it's still not good enough. And this is an interesting test in particular because this is Cockroach playing on Oracle's turf. This is just a 3-node cluster. And despite outages that exceeded the IT resilience expected on a 3-node cluster, the apps in Cockroach recovered more quickly and they stayed available considerably longer. So performance under adversity, this is great. We're marrying the two critical requirements here. But workloads depend on raw performance as well. And with the coming of AI, we can expect a dramatic acceleration. And I think our big conclusion with the scale requirements that are coming as a result of agents is just that databases have to get far more performance out of the same costs and hardware. So a primary goal this year, in addition to all of these amazing resilience advances, was performance optimization. And the results have been dramatic. So the 25.2 release, which came out earlier in the summer, was 50% faster than the 6 months earlier release, which is 24.3. And that means that you get 50% more throughput for the same hardware. And all you have to do is upgrade to get it. So I hope you all do that more quickly than normal. So that's kind of where we are today, meeting the moment as we see it. But what about tomorrow's applications? And AI has certainly taken over the conversation here. And we've resisted becoming an AI database and that sort of thing because the reality is OLTP is extraordinarily hard, and it is going to still be extraordinarily hard in 50 years. That's my contention. But the rise of AI chatbots and then coding tools, I think it's pretty clear to everyone that the AI era has certainly dawned on us. Now, we're seeing this year the rise of and the very popular expounding on this idea of agentic AI. And these aren't just smart assistants where there's a human directly in the loop. It's this promise that we're going to be able to set these AI agents off and they're going to achieve results and outcomes autonomously. And pictured here is a pretty familiar agent pattern where a human interacts with an agent, this thing's sent off, and then it loops, it interacts with the environment. Ultimately, that means it's interacting with APIs and with applications, which are in turn interacting with the backend database. So what does it mean for data systems? And this is the key here, right? It means a lot more pressure. So if you zoom out and you look at the world today, applications almost universally follow a simple pattern, which is true whether you're running a bank, whether you're running a food delivery service, or whether you're running a media company. The users interact with your application, the application interacts with the database. But agentic AI is introducing considerable new pressure into this. Now we're looking at AI agents operating at scale, autonomous active participants, and they don't sleep. Right? They query all the data they can. They do it exhaustively. They do it repeatedly. They operate at machine speed. And unlike humans, where we have 8 billion, maybe going to 10 billion, people think that's going to start to go down from there. There's no hard limits on the proliferation of agents. I don't know that there's a billion running today, but there will be. Then there'll be 10, and then there'll be 100 billion, then there'll be a trillion. There could be 10 trillion. What does that mean for all of our APIs, all of our databases? Well, it means that I think many legacy databases weren't built for this, right? And vertically scaling architectures are going to break without fundamental transformation. Cockroach was designed for this challenge, and these are fast becoming requirements for all successful businesses. So in line with AI, this is something David mentioned, we recently did release a vector search capability. And I'll just tell you a little bit about it because I think it helps set the context for what we had to do to really responsibly introduce this capability to CockroachDB. So vector embeddings are important because of all these advances in AI. And what they are is just numeric representations of concepts. And that could be a collection of words, it could be audio file, it could be images, it could be video, I'm sure many things besides. And why does this matter? Well, the interesting thing about these vectors is that they represent concepts in a very intuitive way. So there are points in a high-dimensional vector space, but points that are close together are very similar related concepts. And that's extremely useful. So just as a very simple example, we have vectors for cat and for dog and for wolf, and they're actually pretty close together in this three-dimensional representation. And that's not surprising, these are four-legged mammals, right? But vectors for banana and apple are distant, but they are also close together because they're examples of fruits. So this is an extremely simplified depiction, of course, but in reality, instead of 3 dimensions, you see hundreds, even thousands of dimensions in vector embeddings. Vector search simply means finding these nearest neighbors and hopefully doing them very efficiently. If you did a search for kitten, that's not something that's in this vector database, but it's going to find cat as the nearest neighbor, which is still a useful result. So there are plenty of purpose-built vector databases, and vector capabilities have been added to most databases that are on the market today. I'd say that the purpose-built vector databases, you can imagine they're very good at vectors, right? But the problem is that vectors are just one kind of data. And ultimately, to build an application use case, you typically need all the rest of the kinds of traditional metadata. And you want them to have the full capabilities that a system like CockroachDB brings to the market. And by the way, combining multiple databases is quite clumsy for applications. They introduce staleness, consistency problems, significant headaches for the application developers. With Cockroach 25.2, we released a distributed vector index. And the beauty of this, the real differentiation in this, is that it inherits all of the capabilities that Cockroach has. Right? It sort of stands on the shoulders of what we've built with Cockroach. And we had to rely on a lot of cutting-edge research and blend in the different directions out there on the market to truly build a distributed vector index that had all of the capabilities that we were looking for. So we call this C-SPAN, based on some of the research that went into its formulation. And it actually has a list of requirements that are simply not found in other vector indexing systems, in particular scale. We wanted this to go to billions of vectors, right? So in other words, it's just another data type within Cockroach, just like geospatial or the normal relational data you'd put in or JSON objects. You have vector embeddings now, right? It's fully distributed in the exact same way. These things can get very large. It's also just as resilient as it's just another data type in the system. And it respects the same constraints on geolocality. And by the way, if you've got some PII data that has to be in a particular legal jurisdiction as part of your business, a vector on that database needs to respect exactly the same constraints. Like vectors are not some sort of encrypted data. They actually can be reversed. At incredible scale, it's important that these results have a high degree of accuracy. That's another very difficult thing to achieve when you're doing approximate nearest neighbor searches. And freshness. This is also extremely important. If you are going to update your vector index because you've recently inserted something into your database, you want to make sure that that is visible immediately upon commit. And so all of these come together in Cockroach's vector index. And by the way, this works naturally with your SQL queries. So it doesn't have to be expressed separately. This is all part of the whole stack in Cockroach, from the SQL query planning engine and optimizer all the way down to the lowest data storage layers. So I'm almost finished now. I did want to mention 3 enhancements in 25.3, which is the most recently released version of Cockroach. And these satisfy some very popular feature requests from our customers. The first is Oracle is now supported as a source database when migrating to Cockroach with our fetch tools, our molt fetch tool. We also have a more powerful Kubernetes operator, and this takes a lot of learnings from our Cockroach Cloud Kubernetes operator. So we're kind of merging these two things. And the idea here is we're going to bring considerably more powerful features of Cockroach to even our self-hosted customers. And then on the security side, this has been our most requested security feature for quite some time. We've enhanced user management with the integration on Active Directory and LDAP. So I wanted to thank everyone again for being here today. You are definitely the reason that we are building Cockroach and continue to innovate and push the bar. And I'd love to connect with as many of you as possible, so please don't be shy. Let's keep the conversation going. And together, let's continue to build the future of databases. Thank you.